The update that just came in is completely unexpected. New images of 3I Atlas from Spain, Thailand, and Norway have been released, and all of them revealed the same unusual pattern. It's not showing signs of breaking up or falling apart, but something different altogether. Let's take a closer look. The first clues came from a long-exposure luminance shot taken on November 22nd from a remote observatory in Spain. In the raw frame, background stars stretched into thin streaks as the telescope tracked the object's motion, but the center of 3I Atlas remained so perfectly fixed and symmetrical that it looked almost artificial compared to the distorted star field behind it. Observers immediately noted that if 3I Atlas were undergoing fracturing, the kind often seen when comets or icy bodies near active states, the core should exhibit distortions, multiple intensity peaks, or elongated brightness signatures. Instead, the central structure was astonishingly clean, compact, circular, and dead-centered. Even before enhancement, the distribution of light at the core appeared too consistent for a body in distress. But the real surprise came when analysts compared the new frame against the previous batch of observations from weeks earlier. The faint asymmetric forward glow, previously soft, diffuse, and somewhat irregular, had sharpened unmistakably. Something about the object's forward axis emission was becoming more defined, rather than weakening or smoothing out. For a typical comet, the outer coma or halo tends to become more chaotic over time, especially if sublimation accelerates or if structural integrity falters. But with 3I Atlas, the pattern was inverted. The central object remained stable, while the surrounding structures grew more active and complex. Only days later, a second set of observations arrived from Rayong, Thailand. These were captured under imperfect conditions, thin, fast-moving clouds and moisture interference, but the images still managed to reveal the same core intensity shape seen in Spain. After enhancement, the glow formed nearly a perfect circle and at times resembled a ring of highly uniform luminance. What set the Thailand frames apart, however, was a layered halo effect surrounding the center. Instead of a single diffuse cloud, the halo appeared as stacked shells, with brightness gradients showing a stepped pattern rather than a smooth fall-off. The similarity between Spain and Thailand surprised researchers more than the differences. Despite the disparate environments, Spain's dry, stable air versus Thailand's humid, turbulent conditions, the brightness curves aligned almost identically. Two independent observers, thousands of kilometers apart, had captured an object with a symmetry unlikely to emerge by chance. It was the kind of consistency you would expect from a controlled system or a highly stable astrophysical body, not one shedding material into space. For astronomers studying transient interstellar objects, such global agreement often signals a real structural behavior rather than an observational artifact. The Norwegian observations, however, shifted the conversation from puzzlement to urgency. Captured under Bortle 4 skies with only about an hour of exposure time, the frame revealed a tail structure much clearer than expected. It wasn't just a straight dust trail drifting behind an object under solar radiation pressure, it had begun to curl. The faint, graceful twist along the tail suggested that material was being ejected unevenly while the object rotated. In other words, 3I Atlas wasn't breaking apart, it was spinning and shedding matter with a rhythm, rather than in a chaotic burst.
Rotation is common among celestial objects, of course. Comets tumble, asteroids spin, and even fractured fragments can rotate irregularly as they drift apart. But rotation alone doesn't explain the combination now emerging from the global imagery. The stable core, seen in Spain, the nearly perfect circular intensity pattern seen in Thailand, and the curling tail captured in Norway pointed to a coordinated behavior, a central body maintaining near-perfect symmetry while its outer layers expanded and twisted outward with increasing clarity. Shortly after these observations spread among the astronomy community, a wide field shot from Virginia added yet another layer to the mystery. The image was faint, its extended exposure barely teased out the full length of a distant tail, but what it captured was unmistakable. A remarkably long, thin, structured line of material trailing behind 3I Atlas. This tail stretched far beyond the lengths recorded in earlier exposures, and yet, even with its considerable extension, the central core in the image remained perfectly intact and circular. The contrast between the sprawling, evolving halo and the pristine core was becoming difficult to ignore. When astronomers began lining up all four sets of images, the Spanish core, the Thai halo, the Norwegian twist, and the Virginian extended tail, an unusual pattern crystallized. The halo radius was expanding at a pace faster than the earlier projections. The forward glow, previously subtle and barely noticeable, was now intensifying and sharpening. The tail was gaining length and definition as though being stretched or guided by a persistent rotational influence. Yet through all these evolving features, the central structure refused to change shape. It did not distort, elongate, or shift in brightness distribution. It stayed perfectly circular, perfectly symmetrical, and perfectly consistent. This stable symmetry is what most observers now consider the most anomalous feature. In standard comet dynamics, symmetry breaks first. A nucleus under stress fractures irregularly, causing brightness to shift unpredictably. Tail structures become chaotic as dust and ice disperse. Halos lose smoothness as jets erupt from different sides. But for 3I Atlas, the opposite was happening. The outer layers showed evolution and activity, while the nucleus remained almost unnervingly stable. To some researchers, this suggests a rotational behavior that is distributing ejected material in a controlled pattern, perhaps due to a uniform surface composition or a consistent rotational axis that has not wobbled despite solar heating. To others, it points to an internal structure more resilient than typical icy nuclei, possibly even a mixed composition of ice and rock, or an unusually cohesive mass capable of preserving symmetry while shedding its outer layers. There is also speculation that the halo expansion's accelerating pace hints at a thermal or chemical response triggered by its close approach to sunlight. If the object contains unfamiliar volatiles, compounds less common in solar system comets, it may be undergoing reactions that produce the layered shell structures observed from Thailand. Meanwhile, the curling tail could be the result of complex dust dynamics, influenced by the object's rotation and the solar wind acting on fine particles. Whatever explanation ultimately proves correct, the unusually stable core remains the focal point of intrigue. Astronomers emphasize that an interstellar object maintaining such consistent symmetry across multiple international observations is rare enough to demand attention. Symmetry suggests cohesion. Cohesion suggests a body much more intact than originally assumed. And combined with its unexpected behavior of its halo and tail, 3I Atlas is beginning to resemble a category of object that doesn't quite line up with known comet profiles. Adding to the anticipation is the expected release of NASA's next wave of high-resolution imaging. These data will provide the closest, sharpest look at the object since its discovery. If the global observations hold true, the new NASA frames may show details that smaller ground-based telescopes simply cannot resolve. Structures within the halo, jet patterns, or even subtle variations in the object's rotation. Scientists hope these images will help answer whether the shell-like halo layers are truly stacked material waves, whether the twist in the tail indicates stable rotation, and whether the core's symmetry is a sign of an unusually strong internal constitution or something even stranger. For now, all that can be said with certainty is that 3I Atlas has defied the most common expectations for an interstellar visitor. It has not fractured, dimmed unevenly, or displayed the erratic instability typical of small bodies under solar heating. Instead, it appears to be maintaining its structure with remarkable precision while exhibiting dynamic, evolving outer features that have captured the attention of astronomers worldwide. As new frames continue to emerge from amateur observers, research observatories, and automated sky surveys, the global scientific community is watching closely. Every new image brings with it the possibility of confirming or overturning the current theories. And given the unusual behavior already documented in Spain, Thailand, Norway, and the United States, the next round of observations could reveal patterns that will reshape our understanding of how interstellar objects behave when they enter our solar neighborhood. Until then, the mystery holds. 3I Atlas continues its journey, spinning, shedding, and glowing with impeccable symmetry, leaving scientists to analyze every photon it reflects. In the quiet spaces between new data releases, one sentiment keeps emerging among observers across the world. This is not a typical interstellar object, and the deeper we look, the more its behavior refuses to be ordinary. As the world waits for NASA's high-resolution imaging, the story of 3I Atlas remains an unfolding puzzle, one that may soon offer answers or just as easily raise new questions about what travels between the stars.